Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 59. In today's lesson, we're going to look at merge sort. Merge sort's another sorting algorithm. It's another recursive sorting algorithm, so it breaks the problem down into smaller pieces. Sometimes called it's called divide and conquer. So you're dividing up the problem into smaller pieces. So we'll jump into that pretty quickly. I've actually already made the text file and the merge sort, so we've just created them like we've done before. And this is the second attempt at recording. First time I did not have the microphone working, so this is a second attempt. So let's see. So we've created those. The first thing I would like to do, actually, let's look at one thing real quick. If I run this really quickly, let's run it. This has still got quick sort enabled, so 1 million. And if we remember right, it took us quite a bit of time to make the million. So actually get started here. I'm going to fix that first. Let's see. Let's come over to utilities here. I'm just going to split this out. I'm going to make two methods here. A generate array with duplicates and one without. So I thought we would get about the same performance. We do not. We get a much better performance if I do this. So we'll just take this out and remove it. So for any kind of change like this, this would be you would want to profile it. So you'd want to see that it actually does help your case. And the next change I'm going to do as well, you would want to check it as well. I checked these ahead of time to actually see that this works. So over here, we will now pop this to, we'll do a hash set. So we haven't talked about hash set before. I'll use used. We can use new format. There we go. So now we'll grab the random number. Outside of this though. Even better right there. So we'll grab the random number. Then we'll say if use.add random if it is not used though. So now what we'll have here is we'll do the hash set. So we'll talk about hash set more in depth later. Right now you can think of it as a different kind of collection, and it has a really nice property of you can do a contains or add or anything like this, and it's constant time. So you're just adding and you don't have to check if it contains it. The add here returns a true or false. True if the element is added and false if it's already present. So if true, wait a minute, I want this to be the other way around, don't I? So if it is added, yeah, so if it can add to the hash set, so if it can add successfully to the hash set, then it returns true, and then we say it's not already there. And that gets us an array without duplicates. So we'll see that this actually speeds it up. So we've seen how long it took. Just a second. I pressed the wrong one. We won't do that one. Stop. We'll click this one. And then we'll hit a million again. A million or 10 million? Wait a minute. There. 1 million. We'll allow duplicates and we'll run it, and much quicker. So again, I did some testing with this behind the scenes, try to improve it, and that helped. That'll help with merge sort because we're going to find that it's pretty quick as well. I'm going to go ahead and open Excel real quickly as well. Let it be opening up on a different monitor. All right. With that though, we're ready to start looking at the merge sort. So right here's the values we used before. This is the same as we used for quick sort and insertion sort. Close them so I quit going to them. So first thing we do here is we break it down. So merge sort, you begin by breaking down the problem into smaller pieces. Then you build those pieces back up into your final set. So here we have this. So we would pick some kind of midpoint. I'm going to say the midpoint goes to the right or to the left side. So we'll have. So when we split this, we get something like 5, 3, 4, 1, 2. And now we keep dividing. So then we get 5, 3, 4, 1, 2. Now we divide again. 5, 3, 4, 1, 2. So now we're at a point we can begin bringing these back. So when we bring them back, we'll sort them. So here, we'll clear this, and now we'll take these two lists here, the 5 and 3. We'll say, is one of these larger than the other? And which one smaller goes in front? Then we'll combine the other. So there we recombine that section. Now we do it again here, and it'll get this one again. Now we have that, but we don't know which one of these is correct. Instead, we have this. Now we'll combine these. We'll say, okay, 3 goes here. Now which one between the left and right? Now 4 comes next. And then we only have 5 left, and we've got another one sorted. Now we do a split again. Now here, we're not going to do anything smart. This one's technically already sorted. We're not going to do that though. We're just going to 3, 4, 5, 1, 2. And now we'll have to redo those, so then we get back to this situation. We have this array. These two are wiped out. So now we'll say between these two, we take the left, then we take the right. And there we go, we're back to sorted. Now we do it one more time, so this will be for the entire loop. Now we have this. So now they're mostly sorted, so now we just take left, or right, right, left, left, right, and we're sorted. Sorting complete. So you can see we broke it down into smaller pieces, and then we recombine those pieces back up. And that's called a recursive algorithm, and that's what we're going to be doing here today. So it's similar to merge sort, but not hardly merge sort. So let's begin here. We'll do our normal setup. Public static class merge sort. Public static void sort. Int array. So this one, the method here is going to be pretty easy. Let's do look at one more thing. So we're not going to actually do a comparison check here. We can tell from looking at it, the comparisons are easy to read here. So when we do the comparisons, it's always going to do the same number for the same number of inputs. So it's constant. So we're not changing the number of comparisons or anything. It's there. Let's also copy. I already closed it. Let's also copy that text. I keep copying around this guy. So merge sort. So we'll look at why it is, but it's log n, and it's the log n in the worst case, average case, and best case. So it doesn't get any of the benefits that quicksort does, or was it quicksort? No, it wasn't quicksort. It was the other one? Insertion sort. So insertion sort's actually quicker on a best case, but on the worst case and average case is as good as quicksort, and best case it's better. Or in worst case it's better. Sorry, worst. It is not better in memory though. It's big O of n. The reason for that is that we have to create an entire separate sets of arrays as we build through and build up the build up the merging. So we'll see that it's even though it's on paper better, even in the worst case, a lot of times quicksort still is going to be better, and that's why quicksort tends to be the actual built-in sort. Is it often better? There are special cases where this merge sort does beat it though. For one, it's stable. Stable. Quicksort by default, I don't believe was stable. It's also not in place. So not in place. Not in place. There we go. All right. So let's implement it. So for this, we're just going to do a sort internal. We're going to pass it array. We're going to pass it the first position, which is 0. We're going to pass it the last position. That's 1, and we're done. There's our array. Now we have to actually create that class as well, or that method as well. Static void sort internal. So we'll pass in int array, int left, and int right. So that'll be the actual sort. We need one more method, and this one's going to be a little bit bigger. So we'll have static void merge. It takes the array, then it takes an int left, an int mid, and an int right. And what we're going to find here is that I'm using left and right to stand in for the left side of the list versus the right side, the left and right side of an array like this. So this is left, this is right. There's midpoints, and we're putting those together into the merge sort. So we'll begin up here. So first case, if left is greater than right, return. So if it's greater than right, we're done. We're going to use that as our ending condition, so when to quit the recursion. So without that, the recursion would just keep going infinitely and eventually should get that Stack Overflow. So we'll put that in there. Let's grab the midpoint now. So we need to know the midpoint so we can pass it to down this level. So to find the midpoint, what we do is int mid equals left plus right minus left divided by 2. So the reason we go with that one, so a lot of times when you think midpoint, you might think just to do something like maybe divide by 2. So that doesn't get us the midpoint per se. So these are indices. By the way, these are indices. I'm saying left and right, so these are the indices of the array. So let's say we have that 5 positions. So 5 divided by 2 is 2. Plugging in here, we get 0 plus 5 minus 0. 5 divided by 2, which is the same thing. So that one works. What if we do a bigger number? Let's say 100. So 0 and 100. So 0, 100 minus 0. So 100 divided by 2, 50. That seemed to work too. So let's do some. Let's say we're not starting at 0 though. Let's say we're starting. Let's say we have that 50. So 50 on one side for the left's 51, right's 100. Does that still work? 51 plus 100 minus 51, 49. That still works. So there we get 50. If we do it the other way though, 100 plus 59 divided by whatever, we're not going to get the same number at that point. So this is just to be able to get a little more accurate midpoint. And we'll see in a minute or in the other spot, we don't actually need to worry about them being hardly as accurate. All right, let's do the recursion next. So what we can say here, my voice is already trying to go. All right, so the recursive step here: sort, internal, right, left, and mid. The midpoint becomes the new high point, and we do it at right, mid plus 1, and right. So now we're saying, okay, take everything in the left division and up to the midpoint and put it in this sort. Everything above that and to the top in this sort. And you'll do that until left is greater than or equal to right. So at some point, as you keep dividing it, you'll get to they're both 1, 1 or 1, 0 or 2 or 1, something that breaks the loop. That's, you keep dividing it until you're done. The final one is we actually need to call merge. So once we get it all broken down, then we merge it back up. So you can sort of think about it as you go down and down and down, and you get a big tree of values. So you get all the values spread out, and then you merge them back up to a single array. And you can sort of think of it like that instead. So that's actually all the sort internal needs. So now we just need to do the merge. So the merge, not that complicated. I'm going to pull out some values here. So I'm going to say, and you could do this count each time if you wanted to. I'm going to pull it out just so it's easier to see. So I'm going to do left size equals mid minus left plus 1. Int right size equals right minus mid. So we need to do the plus 1 because this side the left side's the one we're letting it take the mid, so it has 1 extra value than the right side does. The right side's just the right minus the mid, so whatever's left on this side. So there, we'll do that. So now we need to create arrays to put stuff in. So we'll say left array equals new int left size. And then int array right array equals new int right size. So notice I'm not using the brace format that I've been using, the simplified initializer. That's because this one does a little bit different. I think we've actually mentioned this before, but I want to see if it lets you show it. But if you put in, when you're creating a new array like that, put in a value there, it tells it that's the size you need, and you don't need to try to resize or anything. So we're not actually putting a starting value of left size in there. We're saying make an array of this size instead. So that's all that's doing. So now here's the fun step. And I actually forgot this when I did it. So when I first tried this, it wasn't sorting, and I had to go actually remember why. Or you actually need to copy the values from your array. So it makes sense. So we need to copy the values from the current array to the left array. I missed one of these. So for, we'll say int I equals 0, I less than left size, I plus plus. Here, we'll remove the braces. So left array at I equals array left plus I. Left plus I. So start at the beginning of the array and work your way up. And that's copying all the values of that one into left array. Now we need to do the same thing, but for right array. We'll do I again. I less than right size, I plus plus. We'll remove them again. You can tell I'm used to actually including braces, and I think I like that better, but I'm trying not to do them for now just to see if we like that better, but the more I do it, I'm not sure I do. Mid plus I, one important point, plus 1. I think that'll get us the right side. So let's make sure this makes sense. So we start at the middle of it. You add I, which starts at 0, so 0. Midpoint got on the other side of the array, though. So it's on the left side, so it was already accounted for on the left. So we do the +1 to avoid the middle. So yeah, I think that makes sense. Now we're going to do something here with the values. So we'll say, no, we'll say int. What would be a good indicator here? Left index equals 0, right index equals 0, maybe. And we need one more one, maybe counter, maybe. It should be left, though. So we'll start at the beginning of where we're merging. Now, while left index is less than left size, and right index is less than right size. Yeah, I think that's what we want. So now we'll say if left array at left index is greater than or equal to right array at right index, array at counter plus, so increment the counter after we're done. It's left array. What? Copilot's annoying me. I think Copilot does different in Visual Studio versus we need to do a ++ here. Does different Visual Studio versus Rider. I think that's where I'm getting mixed up on these. Array at counter ++. What is it even trying to do there? Equals right array. That's actually right. So right array and then increment the right index after you grab it. I think that gets us our array. So I think that's actually almost all the merge we do. The last point, at the very end, there's going to be some values left in one array or the other. So one of these, the size maxes out before the other, and at that point, we need to grab that array. So we'll say while left index is less than left size, then we'll do array at counter equals that, yeah. And now we need to grab it from the right side in case it was the one that remained. Equals right size at right index ++. That should grab all the elements from the remaining array. Right array. So I see something. Let's call counter Control RR. Let's call it current index, maybe. That might be a little better name. All right. So there's us our entire merge algorithm, though. So we get our sizes, we create our arrays, we copy the arrays into the subarrays, and then we merge them. So while the left index is less than the left size, and the right index is less than the right size, then we just grab whichever one's the larger. Once that's done, then there might be some extras left over, so we'll say, let's say something like get remaining values from the sub arrays. Something like that. And that's their merge algorithm. So pretty relatively small. So when you look at this merge sort here, it splits. If you look how many times it split it out, my example here doesn't do a great job of that. But you should get about log n. Like you shouldn't have to do everything. So we did 1, 2, 3. the 3 out of 5, and you should see something similar as you go through. So that's where you get the log from. And then you get into all the individual elements, and then you have to go through all the individual elements, and that's where you get the n from. So n log n. And you see there's a lot of setup in here and different extra looping and stuff. That's where you end up getting that quick sort usually ends up being quicker than merge sort. But merge sort, I always liked the algorithm myself. That it's one of my favorite of the sorting algorithms. It and the next one are probably my favorite too, actually. And I like how this one just how it works because you do the copy, so you create your subarrays, you just loop through them, and you just merge at the end, and that's pretty simple as far as the actual sorting logic, relatively speaking. And I like divide and conquer as well, so I like the feel of that as also. So let's make sure it works though. So make sure we haven't made any problems. So over here, we'll go ahead and Control K, Control C here. We'll do merge sort. And notice we don't have a comparison one here, so we can keep that in mind. So what we should see here is that we can merge sort. We'll say 1,000. We'll find with no duplicates. And array is sorted. And pretty good runtimes. Here, let's do one more thing. Let's do we'll do utilities, print, array. We'll do that real quickly. So let's see what happens here. And this is going to be hard and unreadable probably, but we'll just do 5 values. Sure. We can leave duplicates. So before we have that array. Yeah, that's hard to see just from how big the values are. Yeah, that looks suspiciously wrong. Wait a minute. Let's check that. So here we'll do this. Is it sorted beforehand? So that's a problem if we've got their sort messed up. False. Okay. So yeah, that did. Yeah, so it is false before. Okay. It's just hard to read to actually see what changed. I really don't see anything that changed value-wise. Here, let's wait a minute. Let's turn that down just a second. Let's do we say the limits, we do not. Oh, we aren't using your. We made it quicker, but we didn't use the quicker one. Did we? Oh, here, this is unused. Let's fix this. There we got that. Let's see, let's do this. So accept duplicates is their condition. So we'll say this. We'll do it like this. So we'll say if this is the case, else Else we'll do it without it, and we'll allow negative values. Yeah. Allow negatives. Let's try this again. I'm thinking we have a bug. Yeah, that looks like before, and that looks like after, and they look the same to me. Let's shrink the values down just so we can see this a little better. We'll say max value is 10. That should be a little easier to read, so we'll say 5 values, don't allow duplicates. Okay, that looks more like it. Okay. Yeah, that looks correct. So if we restore that. Five values. Okay, that looks a little better. Yeah. Okay, so not broken. So we were still correct. So there we go. And that's using our new implementation. So now if we plug in 1,000,000. Oh, it's printing them all, but remove those prints. Now if we try it with 1,000,000, we should be reasonably quick. And they're pretty reasonably quick. So there's a submerged sort, and it does seem to be sorting, even though that still looked suspicious on that first one. And went pretty quickly. So we'll go ahead and take that value. So let's go ahead and grab the values. So 97442.5. And we don't have that value on merge sort, so this or quick sort, so that's the only one we have for it. So that was pretty quick. We'll grab the rest of the values hopefully pretty quickly as well. We'll do 10. 1, 0.6, 0.91, 100. Take the values. 2.8, 1.1, 5.43, 1,000. 2,000. Yeah, this is so much, or this feels quicker back than when we did the bubble sort. I think by this point you were starting to see a slowdown. 5,000. 1389.3, 570.60, 666.58. 10,000. 2042, 129.4, 1391.43, 20,000. 3997.8, 1256.1, 2360.93. 50,000. Noticed it was a little slower, but still very quick. 590.763. Now 100,000. I thought I miscounted there for a second. Okay. Here we go. Here's our graph. That sort of looks a little hard to interpret. So these are times. So what we'd be looking for is that the times are growing n squared. And hard to sort of tell from that. Let's turn off the million point. I think it's just make this a 0. Cancel. We'll just do it like this. You can sort of see there that it's sort of growing. That sort of does look a little more in log n-ish. So if we compare that to, say, I think we actually got better performance here last time. There we had 6271. Here we had 8616. So a little more performant than the quicksort was. So both quicksorts beat us. So again, we sort of should expect that. But let's see. Let's run a quicksort against a million now that we can generate a million in reasonable time. So let's do we'll do the first one since it performed better in general. See if it still does. 6. I think it still does. There we got those numbers. Grab Excel. We got 114, so faster there. Minimum though was 59, which was a lot faster, and low was 61. So yeah, quicksort's still the faster of them. If we had 1 million here, just add that here. 59219.8 and 61245.32. There we go. But we sort of see the same kind of graph there for the values. They sort of do the little, they're sort of growing logarithmically, a logarithmic curve. Do we do an example here? Yeah. You sort of see that, just it's very less pronounced than this one is. Sort of hard to tell there too. But we are growing as expected, and it's a lot quicker than anything else. Let's try here. Which one was the fastest? The insertion. Yeah, insertion sort was fast. Let's see how slow it actually goes here, though. If we do Control K, Control C, and let's reopen this one, Control K, Control U. Let's run it with a million. Let's see what happens. Now that we have a million, that doesn't take a year just to generate. Pretty slow, and you can hear my computer speed up. So as we let one run of this one finish, hopefully, so you can see there the two in-log n algorithms we've looked at so far are dominating even the fastest of the n-squared algorithms. Yeah, that's really slow. Nope, see it right offhand. I want to see if it was kicking up from the processor speed or much. Not a lot. Then the cores, one of them looks pretty high, but everything else looks all right, and that one might be the one actually doing the recording. All right. But yeah, you can see here it's still running, still no sign of end in sight. So the insertion sort, even though it was the quickest for, of the n-squared algorithms, was very slow compared to merge sort or quick sort, but for that matter. And that's what you should expect by the growth of functions. That O of n, we can use that. We can say that an n-squared algorithm, in general, for large numbers like this, is slower. And that's what we're going to see for the last one as well. I'll go ahead and spoil the last one. It performs on similar levels to merge sort. It's going to be n log n. It's called a heap sort. And it's going to cause us to learn, or at least look at a new algorithm, or a new data structure. That'll be called a heap. So that'll be the next lesson. It's also a merge, or a recursive sort as well, but it works a little differently. There we go. First value. What is that? No seconds. 116 seconds. So yeah, pretty significantly slower. That being said, that's still 116 seconds is still under 2 minutes. So that's still actually pretty quick for a million values, relatively speaking. I'm going to cancel it here. I'm not going to watch the rest of this. We're just going to cancel. Let's do this. Let's undo quick sort one more time. Let's try this. Now that we got a quicker value here, let's do 1, 2, 3, 6, 7, 8, 9. If we ever generate one, this may be too slow to even generate it. That's a lot of numbers. That's a lot of numbers, and you can actually see the memory actually spike a little bit on that one, but not a ton. I've still got bigger things open in the background. Yeah, that's going to take too long to generate, but yeah. So of the algorithms we've tried so far, quicksort's the fastest. And we'll find in most cases that'll be the case. In worst case, it's actually n-squared, so it won't perform any much better than insertion sort, but in cases that aren't worst case for quicksort, merge sort, or it still beats merge sort. Occasionally, you might run into a situation you want to actually use merge sort those if you're merging lots and lots of values. And that's where I've actually seen it, and actually in practice is merging. I want to say it's about 70 gigs of data, and the algorithm there broke different files into different groups and merged them together to sort them like that. With something really big, sometimes you don't want to do it in memory, so you might want to do it separately in files, and merge sort might make more sense in a case like that. But we'll stop there. I don't know that the other one will ever actually finish. If it finishes, I might just write it down just so we have the number for how long it actually takes to sort it. But we'll stop there. So that's been episode 59 of Programming with Shadow. In today's lesson, we looked at merge sort and implemented merge sort. So the last sorting algorithm we'll intend to start with here is quick sort. I may still want to do a few more sorting algorithms, maybe, but these are the big six, and a lot of the other ones are. There's a major exception, but a lot of the other common sorting algorithms you'll see pop up online are some kind of combination of these. So we'll go ahead and stop there. The next lesson will be heap sort, and we'll look at what a heap is. It's a different type of algorithm, or data structure. I keep saying algorithm, data structure. And we'll see that it's useful for sorting too. And in fact, when we checked for really large values, it's the actual algorithm that the .NET sort actually runs. So we'll save that for next time. So thanks for watching, and have a wonderful rest of your day.